Namaskar. Now in this series, we will go through different uses of NAND gate, NOR gate as a universal building block. Then how to construct the XOR gate using these two gates or any one of them. What is the logic expression, logic symbol and truth table associated with a gate. Then how the XOR gate can be used as a parity generator or checker, and XOR gate how we can use it for the construction of half adder and full adder. Okay. Now basically we are aware about the different types of logic gates. Okay. Now what is the meaning of logic gate? It is the logic device in which the output is the logic combination of input or inputs. It is known as logic gate. We are aware about the three basic logic gates. Now as a revision we will go through these three logic gates. Now the first logic gate which is NOT gate. It is known as NOT gate. Now for every logic gate or the logic device there is the symbol for this. Therefore symbolic representation of the NOT gate is this. Here it is a triangle with a bubble at the end. Then this is input, let it be A. This is output, it is Y. Then for this logic gate there is a logic equation which gives you the relation between output and input, and here I can write Y is equal to NOT of A, or in other way I can represent it as Y is equal to A bar. A bar means it is NOT of A. This is the logic symbol, this is logic equation. Now one more terminology is there associated with every gate or every logic device. It is the relation between input and output. Therefore here I can write this is input, this is output. Typically for NOT gate there is a single input A and the output is Y, and there are two possibilities in input. Suppose the input is 0 or the input is 1. And what about the output? Output is not of A. That means if A is 0 then the output Y is 1, and if A is 1 then the output is 0. Okay, therefore for NOT gate this is logic symbol, this is logic equation, and this is the truth table associated with the NOT gate. Now the second basic logic gate with which we are familiar is the simple gate. It is A and D, that is AND gate. A and D, it is AND gate. Generally it is the convention to represent the logic symbol, logic equation and truth table for two input AND gate. But we are aware about there is a possibility of 3 input AND gate, 4 input, multiple inputs are possible for AND gate, and for NOT gate there is a single input. Essentially there must be one input. Therefore we will continue with the 2 input AND gate. The symbolic representation for 2 input AND gate is this. This is the symbol for AND gate. Let the input is A, other input is B, and the output is Y. Now it may happen that there is third input, fourth input, fifth input. Now what is the speciality of AND gate? The output is high, that is 1 or active, if all inputs are active. Therefore it is AND, that means Y is 1 if A and B and C and D and E, so many inputs, if all are 1 then the output is 1. Therefore the logic equation for this AND gate is it is A and B, or in symbolic or in short form I can write it is A dot B. Dot indicates that it is AND operation among A and B. Okay, therefore it is A and B. Okay. Now while preparing the truth table for this AND gate, we can observe that there are two inputs. Therefore for input there should be two columns. The output is single, therefore this is the output. Here I will write it is Y, input is A and input is B. Now if there is 3 input AND gate, then we will have to have A, B, C, 3 inputs, and then the truth table length will increase. Now what are the different possibilities for input? in binary number system we have observed that if there are two bits for a number, then the possible combinations are 0 0, 0 1, 1 0 and 1 1. Therefore these are the possible combinations for input, and hence I will have to prepare the truth table in this form. Now, as the gate is AND gate, when both A and B are 1, then the output is 1, otherwise it is 0, and therefore I can prepare the truth table in this form. If A is 0, B is 0, output is 0. If A is 0, B is 1, then the output is 0 because A is 0. If A is 1, B is 0, again the output is 0 because B is 0. And when both A and B are 1, then the output is 1. In case of 3 input AND gate, you will have to increase this, and only if A, B and C all are 1, then and then only output is 1, otherwise it is 0. And this is the logic symbol, this is logic equation, and this is the truth table for AND gate. Now in the similar manner we can quickly prepare the truth table, logic symbol, logic equation, etc. for OR gate. The representation of OR gate is like this. This is input A, this input is input B, this is output Y. I can write Y is equal to A or B, or I can simply write it is A plus B. The plus sign indicates that the logic operation between A and B is OR operation. Okay. Now how I can prepare a truth table? Again, as I am considering the 2 input gate, here I will have to write input, here I will write it is output. Output is single, it is Y. There are 2 inputs, and therefore I will write it is A and B. And there are 4 possible combination for 2 inputs, 0 0, 0 1, 1 0 and 1 1. Now what is there? It is OR gate. OR means A or B, then the output is high, and therefore if it is 0 0, it is 0, but it is 0 1, output is 1. It is 1 0, output is 1, and if it is 1 1, output is 1. This is the truth table for 2 input OR gate. Now remember that if there is 3 input OR gate, then I will have to prepare a truth table with input A, B and C. Third column will be there. The possible combinations will begin from 0 0 0 to 1 1 1, and except for 0 0 0, output will be 1 because at least one input is 1, and therefore output is 1 for the OR gate. Now these are the basic logic gates, that is NOT, and OR. Now with help of these two, we can derive several logic gates. Sometimes 2 more gates are referred as the basic logic gates. One is known as NAND, but actually this is not of AND. That means what I will have to do? I will have to combine the AND gate and then NOT gate. That means what I will have to do? I will have to make NOT of AND. That means first of all I will have to implement AND gate, and then I will have to complement the output, and therefore the symbolic representation for NAND gate is, it is the AND gate, and there is a bubble. This bubble indicates that there is a complement of output of AND gate. This is output of AND gate, and the bubble represents it is complement. Therefore if I write here it is bubble, it becomes the NAND gate. Now if input is A, input is B and output is Y, this is typically 2 input NAND gate, then I can write Y is equal to A and B and its complement, and therefore I can read this as it is A NAND B. See, here it is A and B. If I make a complement of that, then it becomes A NAND B. Now actually there is no need to write the truth table separately, because the truth table for AND gate is this, and what I will have to do? I will have to make complement of output Y as a output for NAND gate, but I will write the truth table for NAND gate, and then the next will be homework for you. Obviously it will be the combination of NOT gate and OR gate. Therefore this is input, this is output. There are 2 inputs, therefore I can write here it is A, here it is B, output is Y, 0 0, 0 1, 1 0, 1 1. See, what I will have to do? It is A and B, 0 and 0 is 0, but I will have to take complement of, that is we will have to take a NAND. Therefore here the output is 1 for NAND gate. 0 and 1, it is 0, but I will have to make the complement. 1 and 0 is 0, but I will have to make a complement, and 1 and 1 it is 1, but for a NAND I will have to make a complement and it is 0. Now if we observe these two truth tables simultaneously, here it is not possible, but you will observe that for a AND gate 0 0 0 1, whereas for NAND gate it is 1 1 1 0. It is just a complement of output of AND gate. Now in the similar manner, what I can do, I can combine OR gate and NOT gate. It becomes NOR, that is not of OR, correct? Just I will prepare the I will show you the what is the symbol. It is obviously this is the symbol for OR gate, and then I will have to make a bubble, that is NOT. Hence if it is input A, this is input B, then this is output Y, and I can write Y is equal to A or B, and then I will have to make the complement. In the truth table, as there is no additional space, I can prepare a truth table for NOR gate here. Therefore this is the output of NAND, and this can be treated as output for NOR, correct? Now what about the output for NOR? We will have to make OR and then complement. 0 or 0 is 0, but I will have to make the complement, therefore it becomes 1. 0 or 1, 0 or 1 is 1, but I will have to make a complement. 1 or 0 is 1, therefore I will have to make a complement, and 1 or 1 is 1, and I will have to make the complement. Therefore this can be treated as an output for NOR gate. You will observe for OR gate it is 0 1 1 1, whereas for NOR gate it is 1 0 0 0, and it is obvious because the NOR is not of OR, that is the output is to be complement for the NOR gate. Okay. Now we can treat these 5 gates to be the basic logic gates, but actually these two NAND and NOR are the derived gates. This was the prerequisite. Now what we will have to do? We will have to think about the NAND or NOR gate as universal building block, correct? It is UBB, universal building block. Now what is the meaning of universal building block? We can construct any one gate using either NAND gate or NOR gate. Therefore what we can do, if there are several NAND gates with me, other gates are not available for me, is it possible to construct all the gates? Answer is yes. The interesting answer is yes. How? We will discuss. But before that, as a prerequisite, we will have to think about one more equation, and that is known as De Morgan's theorem. It is again a review of the knowledge with us. Suppose I can write an equation, it is A or B complement, that is the NOR gate, then I can write it as A complement and B complement, which indicates that NOR is equivalent to A complement and B complement. Therefore what is NOR? NOR of A and B, A NOR B is equal to A complement and B complement. In short, I can write break the bond and change the sign. This is one De Morgan theorem. And similarly, A and B bar, that is this is NAND, and NAND is nothing but OR of complements. आता मी वेगळा शब्द वापरला बघा, NAND of A and B is nothing but OR of their complements. Same here I can write, it is A, then it is NAND B, which is nothing but OR of A bar and B bar, therefore A complement or B complement. These two are known as De Morgan's theorem. Now why we are going to discuss something about the De Morgan's theorem? The reason is that instead of discussing all four possibilities for inputs, instead of that I can simplify the logic equation. See, either I can discuss the gate with help of a truth table, or with a logic equation. How we will discuss. Correct? Now I will show you how the NAND gate can behave AND gate. Therefore, I will write here it is NAND as, sorry, not NAND as NOT gate. It is very simple. This is my NAND gate. This input is A, this input is B. And what I will have to do, just if I combine these two inputs, and now if I call this as input, say for example X, X is already, Y is to be used for output, and therefore I cannot use X. Here I will write it is P, suppose. Okay. Then, how can I write Y? Actually, Y is equal to A NAND B. Therefore, it is A dot B bar. Correct? But here A and B are combined together, and that is equal to P. Therefore, I can write this is equal to P and P bar. Correct? But what about P and P? Suppose if I think about a AND gate, which is somewhere here, this is AND gate. If both the inputs are same, that is A and B are same for this case and for this case, then the output remains same. See, it is 0, 0, 0, 1, 1, 1. And therefore, I can write if both the inputs are PP, then the output remains P for AND gate and complement remains as it is. Therefore, you will observe that Y is equal to P bar, and hence this combination or this circuit in dotted is nothing but the NOT gate. The input is P and output is complement of P. Therefore, this NAND gate is now behaving as a NOT gate for input P. It is very interesting. Now I will show you how the NAND gate will behave as AND gate. Now as we are aware about the NAND gate as NOT gate, now it is very simple. I will show you the diagram. Suppose this is a NAND gate. Okay, this is our NAND gate. This input is A, this input is B. And if I use the complement, that is NAND as a NOT gate in front of that, and obviously complement of complement is the input again, and therefore if it is the complement of AND, see NAND is nothing but a complement of AND, and once again if I make the complement, then it becomes the AND gate itself. I will write how it becomes. This is A, this is B. Therefore here it will be A and B complement. And what about this? This is our NOT gate, just I have observed here, and therefore here the Y will be A and B complement is, and again its complement, and complement of complement will cancel each other, and it remains Y is equal to A and B. Therefore this particular combination of two NAND gates, in which first NAND gate is behaving as a NAND gate itself and second NAND gate is behaving as a NOT gate, entire circuit will work as AND gate, and therefore I can say that how we can use the NAND gate as a AND gate. We need two NAND gates to implement the AND gate. Now I will write here it is NAND as OR. Okay, what about we will have to do? We will have to use NAND as OR. How? Again it is very interesting. What about OR? Here I have observed that the OR is nothing but NAND of complements, and therefore what I will have to do, I will have to first make the complement using NAND gate. Therefore I will have to implement the NOT. Using two NAND gates. Here the input is A, here the input is B, and I will provide output of these two NOT gates to one more NAND gate. Therefore you are observing only NAND gates, three NAND gates are there. And how we can write the output Y? I will check. This is the complement, therefore it is A bar. This is again a complement, it is B bar, because here we have observed that if both the inputs are connected together, then the NAND gate will behave as a NOT gate. Both the inputs are connected together, then the NAND gate will behave as a NOT gate. And what about output Y? Here I can write output Y is equal to NAND of A bar and B bar. See, it is A bar and B bar, SA bar. Correct? It is NAND of A bar, B bar. See, for simple NAND gate, what is the output? for simple NAND gate, y is equal to a dot b bar, but inputs are a and b. Now the inputs are a bar and b bar, and therefore I will have to write a bar and b bar the bar. Now according to De Morgan's theorem, if I will have to break the bond, then I will have to change the sign, and hence I can write, if I break the bond, this upper bond, then I will have to change the sign, and complement of A plus complement of B, but complement of complement is nothing but A, and complement of B is nothing but B, and therefore it is y is equal to A or B. Hence this particular circuit of 3 AND gates behaves as OR gate, correct? And therefore I can write it is NAND as OR. Now is it meaningful to write as NAND as NAND? It is obvious, NAND gate behaves as a NAND gate, and hence we can think about there is no need to consider this particular term. But we will have to consider how the NAND gate behaves as NOR gate, therefore NAND as NOR. But somewhere here I have used the NAND as OR, and to make it NOR, what I will have to do? Again I will have to add the complement, and therefore I will give you the circuit, which is very interesting. This NAND gate is behaving as a NOT gate. This NAND gate is behaving as a NOT gate. This NAND gate is behaving as a NAND gate for the complement of A and B. Therefore effectively it is OR gate, and again if I make the complement of that output, then it becomes the NOR gate. Now how I will have to simplify this equation? The equation simplification is very interesting. Here it is not of A, therefore it is A bar. Here it is not of B, it is B bar. Somewhere here it will be A bar dot B bar sa bar, but I can simplify this as A or B, and then here it is y is equal to A or B complement, because this is nothing but a NOT gate, and this is the logic equation for our NOR gate, which we have observed. Typically for NOR gate the logic equation is y is equal to A plus B bar, and I am getting the same situation, correct? Now exactly in the similar manner, NOR gate also behaves as universal building block. Okay, now when I consider NAND as a universal building block, I have mentioned that the NAND gate or gates multiple can be used to construct NOT, can be used to construct AND, can be used to construct OR. These are the basic gates. Then can be used to construct NAND. There is no need to construct this because NAND gate itself behaves as a NAND gate, but we can construct a NOR gate, and these are the derived gates. Therefore all 5 gates can be constructed with help of a NAND gate only, with help of multiple copies. To implement the NOR gate with help of NAND gate, we require 1, 2, 3, 4 NAND gates, but it is fine. Similarly, using several NOR gates, we can implement all the 5 gates. Just I will give you the diagram, circuit diagram, and to write the equation and to check whether it behaves as a NOR gate, AND gate, etc. That will be the homework for you with help of the Boolean equation using the De Morgan's theorem. But one more technique is there. We can prepare a truth table for each and everything. That means suppose here it is A is equal to P is equal to 0, then A is equal to 0, B is equal to 0, and hence the output is equal to 1. P is equal to 1 means A is equal to 1, B is equal to 1, and hence the output is equal to 0, etc. That can be treated as a homework for you. Now how I can use the NOR gate as NOR as NOT? Again it is very simple. Here our NOR gate is there, and if I combine 2 inputs together, then this will behave as a NOT gate. Therefore NOR as NOT gate. How can I write NOR as OR gate? It is very simple again. I will have to begin with the NOR gate. This is our NOR gate, and I will have to make its complement using the NOR gate again. Therefore this is A, this is B, this is Y. Rely on me that Y is equal to A or B. Now if you don't wish to give trust on me, then you can simplify this. This is A, this is B, then you may write here it is it is A or B complement, and the complement again complement, this will be A or B. Similarly, how can I think about NOR as AND gate? Here I will have to write NOR as AND gate. For that I will have to using the De Morgan's theorem, that is here I can not first, therefore I will make A B complement, here it is A complement B complement, and then I will make NOR of them, their complement of complements will be here. Suppose I will write quickly, here it is y is equal to A bar plus B bar cha bar. Now break the bond and change the sign, therefore A bar bar dot B bar bar, and that is equal to A dot B, therefore it is behaving as a AND gate. Now exactly in the similar manner, how we can think about the circuit diagram for NOR gate as a remaining, which one is remaining now? It is NAND gate. Okay, it is fine. This is AND gate. Now further if I make the complement of this AND gate, then it will be the NAND gate. Therefore I will write it is NOR as NAND, and for NOR as NAND I will have to make the complement of input A and B. I will have to make NOR of these two. Therefore up to this point it is A and B, and if I make the complement of that output again, then here it will be A and B bar. This is Y, and that is nothing but the NAND gate. Therefore this circuit will behave as NAND gate, where I am using 1, 2, 3 and 4 NOR gates. Therefore this is NOR as a NAND, and last one NOR as NOR. Actually there is no need to implement, because the NOR gate itself behaves as NOR gate. There is no further construction or further additional circuitry in this case. Therefore in this video we have gone through the how the NAND gate behaves as a basic building block, and how the NOR gate behaves as a basic building block. The statement is a bit confusing. In short, if I will have to mention in a single statement, then I will have to use that. The statement is NAND and NOR as universal building block. This AND is for English, therefore NAND gate. At the same time or along with that, NOR gate behaves as universal building block. But now if I read this AND in capital, then it may be confusing whether it is the logic equation or whether it is in English. But let it be. Therefore we can say that NAND gate behaves as universal building block, NOR gate behaves as a universal building block. Thank you.